A compound pendulum is an extended object and a rigid body that is rotating about a perfectly smooth axis. Now we will deal with the situation of a compound pendulum that is rotating near the surface of the Earth. So the weight of this compound pendulum is its mass big M times little g. That's acceleration due to Earth's gravity. Now we could contrast a compound pendulum with a simple pendulum. A simple pendulum consists of a single point particle of mass m, and it's attached to a string or a wire where we assume that the mass of the string or wire is negligible. We assume that it's zero mass. So a compound pendulum involves many point particles, if you like. A huge amount of point particles that are connected to each other rigidly. Now we looked at the case of a body that rotates around a perfectly smooth axis out in outer space where no forces act on it. So if it was rotating, we saw that it will rotate forever with constant angular speed. And I also mentioned that the force on the object, due to its being in contact with the axle, would lie on a line that connects the center of mass to the axle. I mentioned that, but I didn't actually prove it. The situation is a bit different when we have the case of this rigid body acted on by a force, namely the force of Earth's gravity. So the force on the rigid body, or due to it being in contact with this axle, in general is not along this line. Okay, so to model this problem, we treat this extended object as a single point mass located at the center of mass or center of gravity of the object. Let's suppose that it's rotating in this direction here. So this is at a particular instant of time. So it's rotating clockwise. So let's suppose at this particular time the angle here is theta. Let the distance between the axle and the center of mass be h. Now let's consider the sum of the external torques acting on this object. What about the torque due to R? We're getting the torques, by the way, about the axis. It makes no sense to talk about a torque unless you refer to the axis. It's very important. So the torque due to R, well, let's look at the magnitude of that torque. Well, it's the magnitude of vector R times the perpendicular distance of vector R to this axis. Well, you can see that the line of action of vector R passes right through the axis, so that perpendicular distance is zero. So the magnitude of the torque due to force R is actually zero, so we don't have to worry about its sign or direction because we're just going to get zero. Okay, now the only other force acting on this, well, the only external force acting on it, there are internal forces acting all the time between the particles to keep it rigid, of course. We forget about those, we just want external forces. That external force is the weight, mg. So let's consider the torque due to this force about the axis. So what we want to do is get the perpendicular distance of the line of action of the force mg about this axis. So here is the perpendicular distance. I've also indicated it here actually. So we multiply the hypotenuse by the sine of this angle to get a side opposite theta here. So this is h sine theta. So let's just write down the magnitude of that first, and we'll talk about the direction in a moment. So we multiply the magnitude of the force, which is mg, times that perpendicular distance, which is h sine theta. So I've explained before, of course, that torque is a vector, otherwise we wouldn't be talking about magnitudes. The convention is that if a force causes an object to rotate clockwise, as I said is what's going on here at this instant, the object is rotating clockwise, the torque is negative. So the torque in all our examples has two directions, positive or negative. So the torque has a negative direction. Now as a vector the torque would be actually into the screen, but as I've explained before, we don't draw that vector, we don't actually show that vector. The direction of the torque is given by a plus or a minus sign, so there's only two directions, and the plus or minus sign corresponds to the actual direction of rotation of the object, whether the object is clockwise or anti-clockwise. Now we consider the principle of angular momentum. It tells us that the sum of the external torques on an object is equal to the moment of inertia of the object about this axis. Again, we're talking about the sum of the external torques about this axis times the second derivative of the angle with respect to time. We used omega to denote the first derivative of theta with respect to time. So this quantity here is actually d omega dt. Now I don't want to use omega here because we're going to use omega to talk when we connect this motion with simple harmonic motion later, and those omegas have completely different meanings. So that's why I don't want to use omega here. So just to avoid confusion, I'll just I won't refer to d theta dt as omega. Now, by the way, I should mention that we have a vector equation here. L, the sum of the external torques, is a vector equation. It is a vector, and it's given by the sign here because we're dealing with an object that's essentially planar, if you like. So the torques are either into the screen or out of the screen. We don't deal with more complicated motions. So that tells us that actually the rate that the second derivative of theta with respect to time could be positive or negative in this position, but in other positions the torque could be positive, this quantity could be positive, and you'll see that the second derivative will have to follow suit. The angular acceleration will have to be positive or negative depending on the position of the object. Okay, so we get this differential equation. Now, this quantity here is just a constant. M, G, H, and I are constants. They don't change. So, you know, this equation as it stands actually is extremely complicated because of the sine theta. We'd have to use a computer to solve this, or numerical methods, but it turns out we can just deal with small angles. So theta is small. Theta is less than 5 degrees. Then, to a very good approximation, sine theta is approximately equal to theta. So we can replace sine of theta with theta. And just as a reminder of why that is so, if we consider, say, an angle theta in here, theta is meant to be very small here, of course. What's the definition of theta in radians? Always when we solve differential equations, when we're using calculus, theta is measured in radians. So theta is the arc length S divided by R. Okay, in this sector of a circle, the arc length divided by the radius. But you can see that that's very close to the side opposite theta in this right angle triangle divided by the radius. So when theta is very small, actually when it's less than 5 degrees, sine theta is very close to theta. Okay, because this red line here is very close to the arc length. So for small theta, for small oscillations of our compound pendulum, we have this differential equation, and this type of differential equation we covered in the section on simple harmonic motion. We dealt with the case of an acceleration term, that's the second derivative, whether it's d2x dt2 in terms of linear acceleration, or here we have angular acceleration being proportional to the displacement. So the displacement here is not a distance, it's an angle. Okay, so the second derivative is proportional to the displacement. So the angular acceleration is proportional to the angular displacement. In other words, if we say double the angular displacement, we will double the resultant acceleration. So we are not dealing with constant acceleration, of course. So the acceleration is always changing. Now we saw in the section on simple harmonic motion that we can write this constant as some quantity squared. Why did we do that? Well, some quantity squared is always positive. Omega squared is always positive, no matter what omega is. Omega itself could be positive or negative, but it doesn't matter. Omega squared is going to be positive. So to ensure that we have a negative constant in front of theta, we put minus omega squared. So this quantity will always be negative. And that's exactly what we want, because the quantity that I've highlighted here is positive. It's always positive. I, the moment of inertia of an object, is always a positive quantity. It's the sum of the products of the masses times the square of the distances. You know, that's always positive because it involves squaring something. Big M is positive, G is positive, H is just the distance between the center of mass and the axle. That's positive. So we want minus something that's positive. So let's call that something omega. Again, this omega is not the angular speed. That's very important. I'm using the letter omega here in the context of simple harmonic motion. You see, the angular speed actually changes all the time for a compound pendulum, whereas omega here refers to a constant. Now, what about the solutions of this differential equation? Well, we saw in a previous video that the solutions are sinusoidals. We can write it as a sine function or as a cos function. It doesn't actually matter. Actually, in this case, I'll write it as a cos function. It's going to be some constant times cos of this quantity here, omega, times t, plus some constant phi. Now, as a reminder, I'll just quickly run through this, the proof that this is indeed the solution of this differential equation. Let's take the first derivative. Well, if you differentiate the cos function, we get minus sine. And we apply the chain rule, so we differentiate the cos function, get minus sine. Differentiating this angle with respect to time will give us omega. It'll give us the coefficient of t. Differentiating phi will give us 0 because phi is a constant. So we get minus omega a. Now let's take the second derivative. Differentiating the sine function gives us cos. And apply the chain rule again. We multiply by the derivative of the angle. The derivative of the angle is omega, and omega is multiplied by this constant out here. So we end up at minus omega squared a. So you can see what we get. We get minus omega squared times all of this quantity here. But this quantity here is just the theta that we started with. So that's just checking that this is indeed the solution of the differential equation. Now let's consider a graph of the solution. So remember, we're dealing with small angles theta. Okay, this approximation, this differential equation is only valid when theta is small, because the correct equation is actually this one here, which we don't have tools for solving, because it involves sine of theta. All right, so let's try to draw the graph of this thing. So let's see what happens when t is 0. So really we're just repeating the section on simple harmonic motion. Let's get theta of 0. So if we plug 0 in for t here, we get a cos phi. So this is the boundary condition for the problem. This is the initial angle. So this is something that we set up ourselves. So we give the problem an initial value for theta. So we could say that this is the situation at t equals 0. Okay, so the angle is, well, I'll get to the name of the angle in a second, but we could just set things up so it's in this position here. So we could actually call this angle theta 0, theta sub 0. So how do we ensure that we get theta sub 0? Well, we just set phi equal to 0, or the phi I should call it. Phi or phi. Okay, so if we set it to 0, then we get the cos of, well, when t is 0, this is going to be 0, this is going to be 0 as well, so we get the cos of 0, which is 1. So we see that a is not phi 0, but theta 0. So that's a typical notation for the initial value of something. Theta of 0 is often written like this. Theta sub 0 means the initial value of theta, or maybe a specific value of theta, but in this case we just consider the initial value. So with this condition here, we've simplified our solution. Okay, we'll set phi equal to 0, and we'll set this term here equal to theta naught. So that when we put 0 in, we get theta naught times cos of 0, which is theta naught. Okay, so this is a valid solution of the differential equation. So now let's look at the graph. So at t equals 0, the angular displacement is theta naught. We can take it to be some positive number, by the way. So, you know, if the compound pendulum is displaced to the right of this vertical line, theta is positive. Okay, and if it's displaced to the left, theta is negative. So these displacements are positive and displacements this way are negative. So we just have a cos graph. Cos of naught is 1, and then we have 1 times theta naught. Theta naught is actually the amplitude. Okay, and we know what happens with the cos function. We can see as theta increases, the cos function approaches 0. That corresponds to the compound pendulum reaching its vertical position. The angle is 0. The compound pendulum then passes through the vertical position, and theta becomes negative, reaches a minimum value, or maximum negative displacement from the vertical, and that value would be minus theta 0. So in the absence of friction, and for the case of small angles, by the way, as well, you know, angles that are less than, again, angles that are less than 5 degrees, this is a very good approximation. So the oscillation will continue, of course, and we just get our cos function. So again, we assume no friction, so the pendulum would oscillate forever. Okay, so what about the period? Well, we know from trigonometry that the period of any sinusoidal function, that's cos or a sine function, is 2 pi over the coefficient of t. So it's going to be 2 pi over omega. And here's our omega. Well, this is our omega squared, okay, that we saw before. So we have 2 pi over the square root of this quantity, the square root of mgh over I. Now in a previous video we looked at the period of a simple pendulum for small angular displacements theta, again angular displacements that are less than 5 degrees, so that we could model the system by a second order differential equation that's easy to solve. So in other words, we can replace the sine theta in the differential equation by theta. So we did this in a previous video, but the method actually followed closely to what we're doing here. Okay, so let's repeat that, but now we'll use this formula. Okay, so we imagine that our compound pendulum is reduced to a point particle. So if I just go back here, so we imagine all the mass going to the center of mass. So we have a point particle of mass big M at a distance h from the axis. Now the point mass is attached to the axis by some rigid piece of wire. Okay, we ignore the mass of that rigid piece of wire. So that means that we can apply this formula, because we can pretend that our simple pendulum is a compound pendulum, and we can calculate I for it about the axis, and we have h, and just plug them into this thing. So what is the moment of inertia of the system about this axis? Again, I said we ignore this rigid wire. Its mass is essentially 0. It's negligible, so its moment of inertia about any axis is 0. So the mass of a point particle about an axis is just the mass of the point particle, which we said is equal to the mass of the compound pendulum, big M, times the distance squared, times h squared. Okay, we're just dealing with a point particle. That's the only particle. We don't have to sum anything else because there's only one particle. Grand, so now we can just fill into this formula. So we put mh squared on top, and we have mgh underneath, and notice what happens. The m's cancel out, this h cancels out, and we have h on top. So we've retrieved the period for a simple pendulum, and in a previous video we used the letter L instead of h for the extension of the pendulum. also as a reminder, notice that the period of a simple pendulum for small theta does not depend on the mass. Okay, it doesn't matter how big the mass is, the time taken for one complete oscillation, that's the period. So to go from, say, maximum positive extension to maximum negative and back to maximum positive is given by this quantity here, independent of the mass. Now, if you have to remember this formula, a useful thing to keep in mind is the units. Okay, so if you mix up where these various pieces go, you can just realize that the units of the periodic time are seconds. So let's look at the units of this quantity. What are the units of I, the moment of inertia? Well, we know that the moment of inertia involves summing mass elements times squared distances. Well, you know, in the limit, this would involve integration. The sigma would become an integral sign and so on, and mi would become dm. But basically, the units are kilograms times distance squared. Well, that's meters squared. Let's look at the units underneath. Well, the mass of the object has units of kilograms, of course. G is an acceleration. Its units are meters per second squared. H has units of meters. So notice that the meters squared and the meters cancel underneath, so do the kilograms. Now, what about the units of 2 pi? Well, 2 pi is just a constant. It has no units. It's dimensionless. So you can see that we end up with, if I just look at this bit here, we end up with the square root of 1 over s to the minus 2. Well, that's just the square root of s squared, which is s. So if you're trying to remember this formula and you're not sure where these various pieces go, remember that you have to end up with units of time, seconds.